come a curved ball curves?
Well, let's find out. In order to understand why a curved ball curves, we first have to look at the Bernoulli effect. Now, the Bernoulli effect was first described by Daniel Bernoulli, and it really dealt with a flow in water. And air is a fluid just like water is. So we can use the exact same effect, and the most common example is an airplane wing. Airplane wing is flat on the bottom and curved on the top. The reason it is because as the air comes towards the wing, the air underneath has a nice easy path to go over through the wing, and the top part has to go over the top of the wing. Well, as this air goes over the top and it splits and it meets up back at the back edge of the wing again, it is moving faster, which creates a low pressure area. So this low pressure area down here is a higher pressure area, causes lift in the airplane wing. Well, when we have a ball traveling through the air, it isn't this nice smooth flow. This is called laminar flow. And laminar flow is when it's nice and aerodynamic. When we have instead a flow comes in, it hits the front surface of the ball, and it has to flow around the backside of the ball just like the airplane wing. Well, this isn't nice and aerodynamic like an airplane wing, so in here we get all kinds of what are called eddy currents, and it's very turbulent. Hence called turbulent flow. Now, this is why we can use our other really famous example of Bernoulli's effect of taking a ball, putting it in an airstream, and it stays in the airstream. First, we're going to see what happens when you put a smooth ball into an airstream. Notice how it stays in the airstream even though it's wobbling around. We've seen a smooth ball traveling through the air, but a baseball isn't smooth. It has seams on there. In fact, the stitches, there are 108 stitches in a baseball. And these grooves or stitches on the baseball tend to catch the air. Now, there's a person by the name of Gustav Magnus who first described this effect, and it's appropriately called the Magnus effect, that when a ball is spinning, well, let me just show you instead what it looks like when a ball is spinning. Since we can't see airflow, here's a airflow with some smoke added into it, and we have a spinning baseball. So here we can see that really rough air, that turbulent air. Here we can see that on this part it's moving faster over the top because these are closer to each other, these are further apart. So we can tell that the ball is spinning in this direction. Since the ball is spinning in this direction, it's creating a low pressure area up here, a high pressure area up here, and causing the ball to go up. So let's take a look at what happens when we spin the ball. Now we'll see what happens if we give the ball an initial spin like a baseball would.
Would it work with a real baseball?
I don't know. Let's try it. Nope, too heavy. For that, we're going to have to kick it up.
Go.
So for this, we're going to have to use our Steel BG50 blower powered by VP Fuel 50-to-1 premix. And now the ping pong ball. Thank you for watching Kicked Up Chemistry. Why a Curved Ball Curves, explaining Bernoulli's principle and the Magnus effect. There's some really great videos out there, especially ESPN Sports Figures that does a great job with Bernoulli's effect, so I didn't go real deep into that. If you like the video, click the like button down there, click subscribe, and we'll see you next time.